we had discussed groups in the abstract. Let's get a little more concrete. Let's look at a bunch of examples so that we have some things to hang our hat on. My favorite part of this is that you've seen almost all of these examples in other places. My favorite abelian example. Are the integers mod n? Pick a number. I don't care what number. The set Zn consists of the integers 0 through n minus 1. And our addition is defined to do normal addition mod n. But really, because I'm only working with the numbers from 0 to n minus 1, we can actually define this as a piecewise function. The biggest possible thing you could add in this group is n minus 1 to n minus 1. Which is never bigger than 2n. So you're really going to be stuck with, at most, you have to subtract off one value of n. Guaranteed to be between 0 and n minus 1 with your answer. So that's convenient. I should verify this as a group. What are my 4 verification steps? Say again? Is it closed? Is it closed? If I added integers, I get an integer, right? If I add 2 numbers in this set, do I get another number in this set? That's why I look at this version of the definition. Adding n minus 1 to any other number except 0 is going to give me something bigger than or equal to n. When I subtract an n value away, I'm back between 0 and n minus 1. And so they can never get bigger than 2n, never subtract more than 1n. So it is closed. All right, we called that property 0. I keep calling that property 1. Property 1 was, what was property 1? That was associative. So how do I do a proof that this is associative? The unfortunate part is that to prove this is associative, I have to do 2 calculations. And I have to show that I get the same result both times. And that's not trivial. But I am going to say that I can cheat. How can I cheat? I can tell you with 100% assurance that this calculation is in chapter 4 of the discrete text. So I've done this before, even if I don't remember it. Or at least I've seen it before, even if I don't remember it. But I can also say, hey, wait a minute. This is really regular ordinary addition in the integers. I know that's associative. And then there's that extra subtraction there, right? At best, there's this 1 extra or 2 extra, because I'm doing it twice, subtraction. And all of the arithmetic in the integers is associative. So maybe I can say, because I'm working with a subset, I inherit that associativity. That actually works. So I can do this calculation the long way. I don't want to. I'm not going to. I'm going to say, hey, wait, this is integers. Integers works this way. I'm good. I promise we'll go through a rigorous proof of that idea in a little while. I'm sorry, I can't help you from up here. Well, let's figure out what that inherited idea really looks like. We'll get there. So, closed. I'm going to make the assumption it's associative. What's next? Is there an identity? Well, this is addition. Do we have an identity? I hope so. You add 0 to a number, you don't change it. And that works for all of the numbers between negative infinity and infinity, which means it definitely works for the numbers between 0 and n. I like that. So we do have an identity. Do we have inverses? Because that's our next one. We don't, I'm in trouble because I started with this as my favorite example, which means I hope it works.
Would be like the inverse would be like n minus a plus b.
Each element has its own inverse, so I'm not sure it's n minus a plus b.
We find the inverse by doing a plus question mark equals 0.
Right, but in this case, that would tell me I should get a negative number, and I'm doing my addition mod n. So while I agree with you, Noah, I think Reese has something to go with that as well. How do I put those two ideas together? I'm going to make your life easy. There's a dial clock in the back of the room. I want you to imagine that instead of a 12 at the top of the clock, you have a 0 at the top of the clock. Then that is Z12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How do I get 3 inverse? There's no negative 3 on the clock, right? What do I add to 3 to get back to 0?
Maybe mod of 3, or like 3 mod of 3 or something.
I'm only working mod 12 because I've already established I'm working with the clock. So I've already established my 12 as being my mod. If I go to mod 3, I'm dividing by 3 and looking at remainders. I want to stay in the 12 universe.
I mean, subtract 12 minus 3.
Aha. It's 9 hours before 12 if I'm at 3, right? There's 9 more to go to get back up there. And that's n minus a. So not n minus the sum, a inverse is n minus a. Because if you add any number to that, you're going to get n, right? But according to our operation, if you get n, you take a plus n minus a plus whatever minus n, that gives me 0 again, doesn't it? So every time I do this arithmetic, a plus n minus a, I get n. Subtract n, I get 0, which is my identity, which is exactly what I want. So on my clock, 1 and 11, 2 and 10, 3 and 9, 4 and 8, 5 and 7, 6 in itself. Oh, 0 in itself. So this works. I did say I wanted abelian. Well, my addition is definitely commutative. No matter which way I do that, I know that if I add regular numbers and switch the order, it doesn't matter. All I'm doing is either doing this and or subtracting n, right? That's this definition right here. A plus b is the same as b plus a. A plus b minus n is the same as b plus a minus n. So that's going to work both ways. Let's pick a nice small number. Let's look at Z3. Colin, you ready? Let's make a table. I might as well, it's small enough of a group, I can write out the group table for this. Using addition mod 3 as my operation, I have this, which y'all know how to add. So fill in the table. 9 items. Adding 0 doesn't change a number. 1 and 1 is 2, 1 and 2 is 3. There is no 3 in this universe. 1 and 2 is 3. 2 and 2 is 4. There is no 4. It must be 1.
Wait, why, so why would we put a 0 when it equals 3 and a 1 if it equals 4? Because it only goes up to 1 and 2.
As soon as I get bigger than 3, my addition rule changes. I have to subtract 3 from my answer. So if I get 3, I subtract 3 from that, I get 0. I get 4, I subtract 3 from that, I get 1. The only numbers in existence, imagine a clock that only has 0, 1, and 2 on it. Take 2, go 2 more hours forward. So 0, 1, 2. Add 2 more, I'm at 1. Does that help, Ben?
Yeah.
Wonderful. Go back to Tuesday. The table we drew on Tuesday with EA and B. Look at that table. What was the rest of the table in there?
Yeah.
What I've just written with those little marks across the top there is a 1-to-1 and on-to function from the set 0, 1, 2 to the set EAB, right? Tables are exactly the same. If you change every 0 to an E, every 1 to an A, and every 2 to a B, they're exactly the same table. These are isomorphic. There's only one group of size 3. It always looks like this. Which means, if you have any group of size 3, it's automatically abelian. Because it's got to look like this, and this is abelian. What? No, I get.
So is that enough proof for it to be abelian?
The proof is in the table here.
Yeah,
Abelian,
so
right?
that would be enough.
1 to 1, 2 to 2, 0 to 0. That diagonal symmetry absolutely is enough. If you have a complete layout of how the group works, you can tell me right away whether or not it's abelian. Yes?
How do we know if the graph is like isomorphic in this case?
Oh,
But
the function.
the
The
function-
function is an isomorphism.
Yeah,
So the function here, phi, goes from the set 0, 1, 2 to the set EAB, and phi of 0 is E, phi of 1 is A, phi of 2 is B. That's 1 to 1 and on to, right? Does it preserve the group action? If I were to say, you take two numbers here and add them, you take two symbols over here and star them, you get the same result here as you do here. Well, since the tables match up perfectly, I know that's true. Phi of x plus 3y is equal to phi of x star phi of y. So the way this operation behaves, addition mod 3, is the same as the way this operation star behaves in its set of things.
so say if we were given the problem and we didn't know the graph of EAB.
Okay.
How would we know that this graph is 1 to 1 and onto without knowing the second graph? Did we just make the second graph based on the first graph?
Exactly. I could actually do this two different ways.
Okay,
Because what I did is I put phi of 1 as A. I could just have easily said phi of 1 is B. But then my table wouldn't look right over there on the other side, would it?
yeah, it would be the same.
The A's and the B's would be
Yeah.
swapped. But if I rearranged the top, instead of going EAB, I went EBA. Then it would line up exactly the same, wouldn't it? But wait, there's more. Here are three complex numbers. I promise you I didn't pull these out of my ass. I'm going to ask you for a little bit of trig. In the complex plane, where I would draw the real part of the number on the x-axis and the imaginary part of the number on the y-axis. Where, hang on a second, it's not 0.
Both of the 1/2 supposed to be negative?
Yes. The only difference between the number other than 1 is the plus or the minus. On the second part, the I part.
Yeah.
They're both supposed to be negative there. Where are the three dots that correspond to those three numbers in the complex plane?
One on the real axis. One 1/2 left, and 3, square root of 3 over 2 up. And then 1 left, 1/2 down, square root of 3 over 2.
You either have to remember some trig, or you have to go back to Calc 2. Let's do a coordinate change. You did those in X and Y, then. What if I asked for you to do them in polar? Oh, man. Chapter 10, Calc 2, we did polar coordinates, right? We did them in the unit circle. So what angles do these make?
Would the 1 be 0?
Yes, absolutely. That's the easy one. That's 0. I won't even make you do them in radians. We can do them in degrees. I should force all of you to tune as the trig students so you remember this crap all the time. Okay. if my x is -1/2, and my y is square root 3/2, I need a radius and an angle to get the polar coordinates, right? How do I get the radius? Pythagorean theorem. 1/2 squared is 1/4. Root 3/2 squared is, add them together, you get 1. That dot is a distance of 1 unit away. So that's again a radius of 1. What's the angle? Well, I need something whose cosine is -1/2/1. And I need something whose sine is root 3/2/1. So cosine of 1/2, sine of root 3/2, what angle is that? Six degrees. Wait, I'm in the second quadrant. It's not 60 degrees, 120 degrees. Okay, wait a minute. If that y value is negative, then I take that same image and flip it over, don't I? So what's the angle of the point down there in the third quadrant? These are complex numbers. Under multiplication of complex numbers. That's a closed set. If you multiply any two of these three numbers together, you get one of the other numbers. If you multiply these two together, you get this one. Because those are complex conjugate roots. This is closed. Multiplication of complex numbers is associative. Do I have an identity? Do I have an inverse? If I multiply this one by this one, I get 1. So these are inverses of each other. And one is its own inverse. Son of a... This is a group! Under multiplication. It's a group of order 3. It's got to have a table that's going to look like that. Now again, I did not pull these numbers out of thin air. I'm going to give this group a name. I'm going to call this group U3. Hey, wait a minute, we used U4 last time. There's a relationship there, I promise. But what that means is I have a decision to make. Clearly, if I'm going to build that isomorphism, Noah, I need to decide which numbers are going to go to which numbers, right? If this should be 0, 1, and 2, then one of these numbers should be 0, one of these numbers should be 1, and one of these numbers should be 2. At this point, my brain says, I should think about the properties I'm trying to match over, right? Up here, 0 was my identity. Down here, 1 is my identity. So I think it makes sense for me to have the correspondence connect the identities. So my map phi from Z3 to U3 should work like this. And now I need you all to make a decision. Which of my other two numbers is going to go with 1? There really doesn't have to be a reason for it. It's literally going to make no difference. Okay. One with the plus or the one with the minus?
Plus.
Okay. If we're going to do that, then the only thing left to make this a 1-to-1 and onto map, this one has to go to the other one. Right? So, now that I've set this up, Noah, I can say, I think it should work like this. And now that we've made the decision, I can decide to put those in the same order, 0, 1, 2. And I should be able to multiply my complex numbers and see what happens. Ready for the best part? I do complex numbers on here. My calculator has a complex number mode. There's even a little I button right down here at the bottom, right above the decimal point. So as long as I set my calculator to be in complex mode, I can ask it to do the multiplication. Negative 0.5 plus square root 3 over 2 I times negative 0.5 minus square root 3 over 2 I. I'm going to multiply these two together. That'll be this block right here. I don't have to do it by hand. If I multiply this one by itself, so there's the top number, right? That's this one. Let's square that. I get the negative 1/2 minus the number. If I take the one with the minus sign in it in the first place, and I square that, I get the one with the plus in it. $64,000 question. Does my table match? There were 3 zeros in my table. For the addition mod 3, where were the 3 zeros? Here, here, here. There were 3 ones. there were 3 2's. It's exactly the same table. And Noah, quite literally, I had no way of knowing which way I was going to try and do it, but I made to line them up in similar fashions. Questions? I freely admit to really, really, really liking complex numbers. My research work is in complex numbers. The majority of my graduate work, I love those things. But what I really like about them is dealing with them in polar coordinates. Because it turns out that if I think of these in polar coordinates, I can steal a whole bunch of trig identities and make my life a lot easier. So let's suppose I have a complex number, which I will call z, and it's got an x part that's a and a y part that's b. Then I can rewrite this. Those are my polar coordinate pieces. Another way to think of that is to say I want to let A equal r cosine of theta and B equal r sine of theta. And those are exactly the same transformations we used back in chapter 10 in Calc 2, polar coordinates. Well, it turns out that if I take 2 different complex numbers and I multiply them together, like that, I could do that by doing the distributive property, right? A times C, B times BI times C, so that'd be BCI, ADI, and then BI times DI. Wait a minute, I got to get an I squared there. What's I squared? So that really makes this AC minus BD. There's the real part. And then AD plus BCI. So multiplying complex numbers gives me another complex number, right? But if I replace A and B by r cosine theta and r sine theta, and I replace C and D by their versions of r and theta, I could do the same thing here, right? Yes.
What is that after the second R?
1. I started to write 2 and then realized it was wrong. It should be 1. So the first one is r1 and theta 1. The second one is r2 and theta 2. I could do all the same junk, right? And I could multiply everything through and gather all my like terms exactly like we did up here. But notice that I'm going to have an R1 and an R2 in every single one of those calculations, aren't I? So really, I could factor that out, and I just get an R1, R2 in front of this whole thing of trig. And now, to make my life easier, I'm going to put the I in front of the sign rather than after it, because I hate having the I after sign, because it looks like it should be sign of the whole thing. Hey, wait a minute. A, B, C, D, right? I know what I get when I do those together. That's an emergency alert test from the school, so a bunch of your phones should be going off the same way I'm on. Well, that's disgusting, isn't it? That is just nasty looking. Except for the fact that Trig rears its ugly head and smacks me upside the back of the head. Says, hey, those look like trig identities. It's been a long time, man. Okay. Turns out, this trig identity is the cosine of the sum of the angles. And that one, cosine, sine, sine, cosine, is the sine of the angles added together. So here is a sneaky ass trick for multiplying complex numbers together. When you multiply complex numbers, you add angles. Holy crap. I've seen this before. Where else have you seen something that when you multiply things together, you end up adding? In algebra, regular algebra.
Exponents.
So the other way to write a complex number is to write the angle as an exponent. I need a base. Well, hell with it. We'll just use E. So instead of writing r cosine theta and r sine theta, I don't bother to write the cosine and the sine. I write E with a complex number and an angle up there. But that means if I multiply r1 e to the I theta 1 and r2 e to the I theta 2, I multiply r1 and r2, and then I add the angles. Isn't that exactly what we just got, working that out with all the trig crap? Whew. So it turns out that those three complex numbers that I picked in that U3 setup, one, which Jalen, you said had an angle of 0, right? Isn't e to the 0 equal to 1? And then negative 1/2 plus root 3 over 2i, that also had a radius of 1 and an angle of 120 degrees. And negative 1/2 minus root 3 over 2i had a radius of 1 and an angle of 4 pi over 3. I switched back to radians this time. But if you want, you can write 120 degrees, 240 degrees. Perfectly fine. Now think of the multiplication. The multiplication becomes adding the angles, right? 120 degrees plus 240 degrees is 360 degrees, except we're adding mod 360. If I do it in radians, 2 pi over 3 plus 4 pi over 3 is 2 pi, and I add mod 2 pi. All three of these points have length 1, right? They're all on a circle. And not only are they on a circle, they make an equilateral triangle on that circle. Way back in trig, a very long time ago, if you got to the section on complex numbers, we covered that there. I don't know if your instructor covered it or not. You know, I didn't in the last time I taught trig by 1 day's worth of material. Noise the hell out of this. This is really cool. But it also means I can work backwards. I'm pretty sure you know how to solve this equation. I'm pretty sure you don't like the idea of trying to solve this equation. You're asking me to take a fourth power and make it negative? That sucks. There's got to be an I in there somewhere, right? How the hell do I do this? I cheat. Over there on the left, instead of writing Z, I write a polar form. I write R e to the I theta. But now I'm going to ask you to do the same thing on the right. What is the polar version of negative 16? Remember, every number in the complex numbers has a version that can be graphed on that complex plane. Where's negative 16? Way over here. What's the radius? How far away from 0 is that? Yay. What angle is that? That one's 0.
180.
I'm going to cheat this time. I'm going to stick to radians, so I'm going to call it pi. So I will rewrite this as 16 e to the I pi. But that's not the only angle that works, right? What other angles might work?
It would be negative pi.
Sure. Because that instead of going this way around, I would go this way around. That would work, right? What else could work? 3 pi minus 3 pi. As a matter of fact, I could add any multiple of 2 pi I wanted to there, right? So I'm going to. There. That's all the possible angles, yes? That's insane. But it is right. That's all the possible angles. A little bit of algebra on the left side now. I have product to a power. How do I distribute that 4?
Would be R to the 4th times E times 4I theta.
Aha, because I have a power of a power, and that means you multiply the powers. I'm actually going to write it as I times 4 theta rather than 4I theta. Promise there's a reason for that. But that is equal to this thing over here on the right. That's 16 e to the I pi plus 2k pi parentheses. You with me so far? It's a hell of a walk. Please notice, I now have a symbol and then an exponential on the left, number and an exponential on the right. That means the numbers out front have to match. R to the fourth has to be 16. And R is a distance, a length. So it's a positive number. That'd be 2. And over there's an exponential. Over here, there's an exponential. That means the exponential pieces have to be the same. And since the bases are the same, that means the powers have to be the same. Cancel the I. And divide by 4. Theta is equal to pi over 4 plus 2k pi over 4. Wait a minute. 2k pi over 4. 2 over, that's pi over 2, isn't it? I asked you at the very beginning to solve an equation whose highest power was 4. How many answers should I get? 4. And they're 90 degrees apart. They're going to make a square. So the first possible answer is 2e to the I pi over 4. K is equal to 0. Actually, let's go ahead and call that Z0 because it'll be where K is 0. And then Z1 will be 2e to the I pi over 4 plus pi over 2. That's 3 pi over 4. And then there are 2 more. Z2 is 2e to the I 5 pi over 4. And Z3 is 2e to the I 7 pi over 4. Now what happens if we keep picking bigger and bigger k's?
The pi would just increase.
Right. So my next one would be 9 pi over 4, right? But that 9 pi over 4 is 2 pi bigger than 1 pi over 4, isn't it? So I've hit the same spot again. If you pick negative values for k, you're going to hit the same 4 spots over and over and over again. That means that these 4 numbers are the roots. If you really want to, you can plug in for cosine of theta and sine of theta, right? So I could tell you that this number, 2 times cosine of pi over 4 plus I sine pi over 4, that makes this first number root 2 plus I root 2. What's Z1? No calculation is required.
Maybe 2.
How is it different? It's very similar. How is it different?
Negative pi over 2. Not root 2/2.
The x would be negative, wouldn't it? So this one over here is going to be negative root 2 plus I root 2. This one down here is root 2 minus I root 2. This one over here is negative root 2 minus I root 2. They're all symmetric. I said it was a square, didn't I? You just have to flip it over.
Do you go for like the first calculation, Z0?
Oh, absolutely. 2 cosine pi over 4 plus I sine pi over 4. Isn't that what the E is? The shorthand for the cosine and the sine?
Yeah, I see it.
In complex numbers, you can find any power or any root this way. As a matter of fact, this method was put together by a gentleman named Abraham de Moivre. And it says you have to take the appropriate root of the distance and then divide the power by that number, the angle by that number. And then you get an equally spaced regular shape. If you did a fifth root, you get pentagons. Sixth root, you get hexagons. Questions? Other than me getting my jollies doing complex numbers, why the hell am I doing this to you? I mean, I like complex numbers. This is cool. But where the hell does that tie in here? Is this set closed under multiplication?
What do you mean close? Like, if you multiply Z0 and Z1, you still get.
One of the z's. That's exactly what I mean. If you take any two of those and multiply them together, do you get one of these? Here's a hint. Do your multiplication with the polar versions, not with the Cartesian versions. If you take two of these and multiply them together, what happens?
We'll still get one of the odd numbers on the non-numerator.
Because I'll add the angles, right? But if I add the angles, what happens?
It'll be a larger number, but it'll still equal one of those. Let's do
Pick one.
2, 3, and 5.
When I add 3 pi over 4 and 5 pi over 4, I get, oh shit. That's not one of the angles. It's even worse than that. If I multiply two of these numbers together, I have to multiply their lengths together. If I multiply two of those numbers together, I get a length of 4. That's not in the set anymore. This set is not closed. This is not a group. Why the hell are you doing this, Dr. Sassmore? What's the only radius that will work? One. So let's consider the set 1 e to the I theta. So that is all the points with whatever angle I want, whose radius is 1. What shape is that? Circle. And it's not just any circle. It's a circle of radius 1. We gave that one a special name. So let's call this U. That's right, Cole. He starts giggling. Yes! U3 and U4 live in this circle. Not only that, U3 are the roots for Z cubed equals 1. And z to the fourth equals 1 gives you 4. If you follow this procedure for z cubed equals 1, you will get 1, negative 1/2 plus or minus the square root of 3 over 2. Those are the cube roots of 1. Because this is the unit circle, we call them the roots of unity. So these are the third roots of unity and the fourth roots of unity. And this is the unit circle. I can think of un as the solutions to z to the n equals 1. Guess what? The nth roots of unity are a group. They're a group of order n. Is
that z to the u or z to the n?
that's an n. Apologies. There. You know what else? We already showed that that's the same as Z3. That can be Z4. That can be Zn. How? So let's suppose I think of my roots of unity. Remember, they all have radius 1. So they all live somewhere on this circle of radius 1. Right? And one of them is 1 itself. Because 1 raised to any power gives me 1. But that means there's one with the smallest possible angle. Let's call that one theta 1. The next one has to be twice as far. By closure, right? If I add that, well, multiply. I multiply this by itself, I get 2 theta 1. If I multiply that by the next one, I'll get 3 theta 1. Then I get 4 theta 1 and 5 theta 1, right? Eventually I get n theta 1. That will have wrapped all the way back around the circle. Be right back at 1. I've drawn a very bad version of this, but we can eventually show that there are exactly n of these. So Noah, how can I make my isomorphism? 1 is the identity, right? So 1 should match up with 0. This one counts my way around the circle, right? When I counted around the clock, I was counting by 1s. So if I match this to 1, I can then use the homomorphism property to build the rest of the table. So in that other color around the circle, I've connected this now to Zn. these groups, even though one is multiplying and the other is adding, these groups behave the same. The textbook actually gives this first one a name. They call it zeta. And that is called a primitive root of unity because it's got the smallest non-zero angle. Primitive root. So in our other example, we had three of them, right? We had 0, 120 degrees, and 240 degrees. The primitive one would be the 120 degrees. And that was the one we made 1. I did it. Here's a sneaky idea. These are complex numbers, right? Multiplication in complex numbers is associative. There's a one-to-one and onto relationship that preserves my action between this and Zn. Zn must be associative too, because it works the same as this. I don't actually have to do the discrete math version of the proof at all. I say, no, this is really these complex numbers and complex numbers associated. That's easy. Now, what we will see in general is that it is often useful to take a group we don't understand very well and relate it to a group we do understand very well. And in my case, Zn is a really understandable group. Zn is a wonderful group. I love working with integers mod n. That's why I did them in discrete. That's why I do them lots of different places. They're great examples. I'm a geek. I love complex numbers. Most of you are looking at me going, this today, lecture, this sucked. Complex numbers are evil. How dare you? I understand that. But you don't ever have to think of complex numbers like that again. Because you can just say, oh, I'm doing the 12th roots of unity. That's my clock. I'm done. There's one exception. The entire circle. That's an infinite collection, isn't it? That's not Z. Why? U itself is also a group under complex numbers, multiplication. Because if I have e to the I theta 1 and e to the I theta 2, and I multiply those together, I get e to the I theta 1 plus theta 2, and that's still going to give me a spot whose radius is 1. That's still on the unit circle. I have an identity. The identity is 1. How do I do inverses? If this is a group, I have to have inverses. I'm multiplying, right? A times A inverse should give me 1. And 1 is e to the 0. So I have e to the I theta times the inverse should be 1, which is the same as e to the 0. This is regular algebra. How do I solve that equation? Yeah, 1 over a is 1 over e to the I theta, right? Wait a minute, I have a power in the bottom. What do I do with it? And if I'm adding angles, doesn't it make sense that the inverse should subtract the angle? It works. Now, this is an infinite group. It also happens to be an uncountably infinite group, because you could have any angle, right? Between 0 and 2 pi. Let's consider the interval from 0 to 2 pi. The whole piece of the real line, right? But notice, I've got a closed end here at 0. I've got an open end there at 2 pi. I'm going to call this the piece of the real line that ends at 2 pi. Starts at 0, ends at 2 pi. That's an interval. I'm going to think about this under addition mod 2 pi. Sorry, that should be an angle bracket. That's a subgroup of the real numbers. Because if you add mod 2 pi, you're always going to get a number between 0 and 2 pi. Your inverse would be 2 pi minus your number, because that would get you to 2 pi, and that would get you to 0. This is isomorphic to u. Because points on u, when we multiply, we add the angles. And all I'm doing is adding two numbers between 0 and 2 pi, and then going mod 2 pi to get an angle again, right? That's what I do when I add angles on my circle. Complex numbers under multiplication are really regular numbers under addition. Because of this twist that multiplying complex numbers becomes adding angles. If you hate complex numbers, you never have to do them again. As a matter of fact, calculations I did on here with complex numbers, my calculator did them in polar automatically. The algorithm for doing complex multiplication switches to polar, adds, and moves back, because adding is easier than multiplying in terms of the number of steps it takes. That's that big O concept from algorithms in chapter 3 in the street. So as much as you hate it, it's built in. The method by which we built that isomorphism between un and zn, I picked 1 the same way we picked minus 1/2 plus root 3 over 2 and said that was what was going to be 1. We let 0 go to 1, and we just made it match up, right? We built it from that basic element, the primitive root. That almost always works. Almost. What do you mean almost? You were asking me about the tables right before class began. I talked about tables of size 4. I think that's one of the homework problems that's due next time. Next Tuesday, I think, in the previous section, where you all have to build a table of size 4. And there's a choice you get to make when you build that table of size 4. If E is my identity, then I am absolutely sure about those 7 spots. The next question is what goes in this spot right here. You actually have 3 choices. Which one has to get eliminated? Which one can I not put? And that's, I can't put A, because A can only appear once in each row and once in each column. So that's either an E, a B, or a C. Which means you could then figure out what the rest of the table looks like for each of those choices. 2 of them match if you shuffle the letters around. The other one's different. So there are 3 tables. 2 of them are really fundamentally the same. And there's that one oddball. And the difference between the 2 comes from your choice of what you put in that spot. Once you make that decision, everything else is forced. So I'm pretty sure the homework problem asks you to make all 3 and figure out which 2 match. But it turns out that the structure is different between those 3 tables. And the one that's different is really kind of weird. Because it can't be built by just taking one thing and building off of it. And your challenge as part of that problem is to figure out why. What's weird about that one table that prevents it from generating? And that phrase will be key moving forward, that idea of generating a group. Every one of these examples has been abelian. What do they look like when they're not? We'll talk about that on Tuesday. So I hope you have a wonderful rest of your day. If you came in late, you owe me a homework paper. I will see you on Tuesday.